Okay, we're going to go through another kinematics problem. This one's a little bit more involved than the two that we watched yesterday, or that you watched yesterday. I recorded yesterday. So we're going to get to it, and I'm also going to do a little bit of work with motion graphs and motion diagrams, just to review those and show how they compare to what we're doing here. So let's start working on the problem first, though. The first thing that we're supposed to do in this first box is to draw a sketch. So I'm going to draw a quick sketch. Why is it still blue? Red. All right. I'm going to draw a sketch of our sprinter. And our sprinter is going to be running. And I'm just going to indicate right here, during this portion, he's accelerating at 2.5 meters per second per second. That's just a reminder for me that that's what he's doing there. And then right here is when he gets to 15 meters per second. And then he keeps running at that constant velocity. So for this whole section, he's going 15 meters per second. And all told, he runs a total of 100 meters. So there's my sketch. It kind of encapsulates all of the information that we know about our problem. I'm going to draw the ground. It seems pretty exploding. So now I'm going to add in a coordinate system. For my coordinate system, I'm going to say that the place that he's starting is 0. Anything going in this direction, since that's the direction he's going, is positive. And it's not really going to be relevant to us in this problem, but anything going the opposite way would be negative. So now that we have a coordinate system and a sketch, we're probably good to move on. Let's start going through our variables. Oh, actually, there's another step we have to do in here, because we have to recognize that something important happens here that didn't happen yesterday. We have a change in acceleration. We're going from 2.5 meters per second to 0 meters per second as soon as he gets to his max speed. What that means for us is that we're going to have to use two separate sets of kinematic equations, because the kinematic equations only work under constant acceleration. If we have a change in acceleration, we'll have to use a new kinematic equation. So when I make my list of variables, I'm going to make one list of variables for the part where he's accelerating and one list of variables for the part where he's going at a constant speed. So I'll have x naught, x, v naught, v, a, and t. And I'll go through, and then I'll need another set of x naught, x, v naught, v, a, and t for this other moment in time. Then let's see. Let's fill in the variables, fill in what we know. We know his initial position is 0 because I defined it that way. We don't actually know this final position, and we might need to know it. So I'm gonna leave that as a question mark. His initial speed is 0 meters per second because that's how you run 100 meters. You start from rest, I think. And he's going to do that until he gets to 15 meters per second. We know that that's where he stops reading. He stops running. And then he's going to be accelerating at 2.5 meters per second per second. We know all of this information from the problem that's been given to us. And finally, how long it takes, well, that's definitely the big question. Then moving into the next set of variables for when he's going at the constant velocity, this is another question mark. We don't actually know where he's starting the 15-minute mark, other than the fact that it's between 0 and 100. We do know that he's going to end at the 100-meter mark. We know that at both the beginning and end of this particular section, since he's going at constant speed, he's going 15 meters per second, and we know that his acceleration is 0 meters per second per second. But we don't know the time, and that's also something we want to know. So going through here, we have several unknowns. In fact, we actually have too many unknowns for some of this stuff. We can't solve all this in one equation in one step. We'd have to use at least 2 steps anyways. So I'm going to need to use one equation here and one equation here at the very minimum. So let's focus on this one here. And I'm just gonna see what I can figure out. Like, what kind of equation work can I do? What kind of numbers can I figure out? And I think what I'm gonna do is I wanna know how long it actually takes for him to get to his max speed. So if I'm trying to find this here, and I don't care about how far he travels, I just want to know how long it takes to get to his max speed. I'm going to start this problem by figuring out how long it takes using this equation. I know that I'm trying to find t, so I could just do v minus v naught equals at, and then say that t divided both sides by a is equal to v minus v naught all over a, which gives me a grand total of, let's see, 15 minus 0 all over 2.5. That's equal to, I want to say 6. Yeah, it's 6. Okay, so it's going to take him 6 seconds. So actually, I know that piece now. I know it takes him 6 seconds to get to his max speed. So I'm going to turn that number around, and now I'm going to use it to figure out how far he traveled during that time. So to figure out how far he traveled during that time, I can, let's see, I'm going to use the, uh, hmm. Actually, why don't I just use the third kinematic equation? I don't even need to use the time that I just figured out, although I could if I wanted to. Plus 2a x minus x naught. Actually, no, sorry guys, I'm gonna do this in a new color just so it stands out just a little bit better. It gets less chaotic. So v squared equals v naught squared plus 2a delta x. Oops, let's not do delta x. That's not how it looks on the formula sheet. It looks like this, x minus x naught. Great. So I know this is going to be 15 squared. Oops, I'm supposed to be doing this algebraically first. So that's 0, his initial velocity. We know his acceleration. We know his initial position, 0. So we can simplify this down to v squared equals 2ax pretty much right away, which means x is just going to be equal to v squared over 2a. And since v squared is 15 squared over 2 times 2.5, that's really going to be 15 squared over 5, which is really just 15 times 3, which is 45. So he's going to travel 45 meters. So now I can go back and fill in that number. I know this is 45. I know this is 45. And I don't really have a ton of space left on my page here, unfortunately, but I'm going to try and sneak it in anyways. I'm going to use the last kinematic equation because now I know all of the distance stuff, and it's just time that I don't know. So that should be good for us to figure out. We can say, let's see, x equals x naught plus v naught t plus 1/2 at squared. All right, what variables can I get rid of? I can get rid of all of the acceleration stuff because he's not actually accelerating. His acceleration is 0, so we can get rid of that term. But that's it. That's all I can get rid of. Everything else is relevant to my problem. So solving it for time, I'm going to subtract x naught from both sides, and I'm going to divide v naught on both sides. So that's going to be 100 minus 45. That's 55 divided by 15. 55 divided by 15. That's not a round number. That's going to be 3.66, I think. Let me double check though. 55 divided by 15. Yeah, 3.66. So this last section here, the time for this one is 3.66 seconds. So our answer to this problem is 9.66 seconds. We had to combine the time for both sections to get that. It took him 6 seconds to get to his max speed, and by then he traveled 45 meters. And then it took him 3.66 seconds to go the last 45 meters. All right, I don't know a ton about running. I don't know if 9.66 seconds is like great, or if it's terrible, or if it's unrealistic, or whatever. But my gut feeling is about 10 seconds to run about 100 meters. That seems like the ballpark. It's not taking minutes, but it's also not taking like microseconds. So we're probably in the right ballpark. So I'm gonna say, yeah, this checks out. I do want to look at this from a motion diagram perspective real fast before I move on. He's doing something kind of like this, where he is accelerating for the first section. So we would have like an acceleration all along the way for that first part. And then eventually he gets to his max speed. Oops, blue please. 1, 2, 3, 4. If I had 100 lines, I could probably do this perfectly, but or 100 squares, I could probably do this perfectly. Maybe I should have. Oh, but then he gets to a max speed. Oops, and actually, this one's wrong. This one should be 0. Then he gets to an acceleration of 0 and just holds that constant pace. So it is here that we use our first set of equations and variables, and it is here that we use our second set. From a drawing perspective, I wanted to do position, acceleration, and velocity graphs. The acceleration graph, he definitely had a positive acceleration at first, at 2.5, and then he had 0 acceleration for the rest of it. From a velocity perspective, he was originally increasing in velocity, and then he leveled off. And this was right at 15. And then finally, from the position versus time graph, I should label these V and X. He was speeding up for a little while, so you would have seen half of a parabola. As his velocity is going faster and faster, he starts having a steeper and steeper slope along this section, but then he reaches that maximum speed. I don't really like the way this graph worked out. Let's try that again. Okay, he's speeding up, but then, so it's still like arcing upwards, but then he reaches the max speed and then he starts going in a straight line. That's when he's reached the maximum speed. That's when he has 0 acceleration. So that's a little bit of how to go about this. We could have actually mathematically solved all of this using the motion diagram or motion graph, but I think this video is quite long enough. So thank you for watching. I hope this helped.